Now to demonstrate the solution of a Bernoulli equation, look at number 24 on page 74 in section 2.6. Recalling that the form of a Bernoulli equation looks of this form: dy dx plus p of xy equals a q of x function times y to some real number power. And we're particularly not interested in this case with n equals 0, 1. We're going to look at other cases. So this particular problem, we can see immediately that it fits this form very nicely, where in this case the n is equal to 1/2. It's actually a fraction, which is perfectly fine. So the substitution that we make for Bernoulli equations is always that v will be equal to y to 1 minus, in this case, will be 1/2 power. Okay? And so that'll be the substitution we make for this problem. And having that, we know that dv dx then, dv dx would be, using the power rule, 1/2 y to the negative 1/2 times dy dx. Or what we could say is that y to the negative 1/2 dy dx is going to be 2 times dv dx. Now, understanding how the relationship between these derivatives exists, given that substitution, is very important, because we go back to the original equation here and realize that if we were to multiply through by, divide by y to the 1/2 or multiply by y to the negative 1/2, what we would have is that this equation really becomes negative y to the negative 1/2 power times dy dx plus 1 over x minus 2 times y to the 1/2 power, because this is to the first power and we're multiplying through by y to the negative 1/2. And then that will give us just 5 times x minus 2 on the right hand side. Now, the reason why we did this is because we see what we're trying to we're trying to transform this whole equation into v in terms of v and x, and we can see the substitution immediately. That what we have now is 2 times dv dx plus 1 over x minus 2 times v, because that's what y to the 1/2 power is equal to 5 times x minus 2. Okay. So if we divide 3 by 2 again, what we would get is dv dx plus 1 over the quantity 2 times x minus 2 times v is equal to 5/2 x minus 2. And now what we have is a linear differential equation where that is the p of x term and that is the q of x term. So this is a linear differential equation. The original problem poses a challenge because of the nonlinear part, but we've actually produced a linear differential equation simply by making this change of variable substitution. So now the goal is just simply to solve that particular equation that we've got. So what we'll do is use the fact that we know that p of x in this case is 1 over 2 times x minus 2, right? Which means that mu of x then, our integrating factor, is e to that power integral dx over the quantity 2 times x minus 2. And taking that integral, we would get that is e to the 1/2 power, 1/2 times ln at the absolute value of x minus 2. And that could be further simplified as e to the ln, the absolute value of x minus 2, quantity to the 1/2 power. So ultimately, what we've got here, just using the property of the relationship between e and ln, is that the integrating factor is simply this quantity, absolute value of x minus 2 to the 1/2, or we could just write it as the absolute value of the square root of the absolute value of x minus 2. Okay. Now, you might have tendencies to think, oh, can we remove the absolute value? Well, depending upon what x is, we don't know if x minus 2 is strictly positive, of course, but x minus 2 that absolute value actually could be the opposite of whatever x minus 2 is. So we don't know if x is positive or negative, so we just need to delete that way because we don't want to risk taking the square root of a negative quantity. So, and if that's still confusing, the point is that the absolute value of x minus 2 is equal to x minus 2 for x greater than 2, but the absolute value of x minus 2 is equal to the opposite of x minus 2 for x less than 2. Okay, so that's why we cannot muck that up. We can't leave that. We can't pull that absolute value. But in the meantime, we can go ahead and solve the equation. Recall for doing integrating factors. In this case, we're solving for v. We could write that as 1 over the integrating factor on the integral of q of x times the integrating factor dx plus a constant. And if we plug all the components in, what we get is 1 over the square root of the absolute value of x minus 2 on, let's say, 5 halves times x minus 2 times that square root again, dx. And with the integration of that, what we would end up getting is 1 over the square root of the absolute value of x minus 2 times the quantity absolute value x minus 2 to the 5 halves power plus c. Right? Which could be rewritten as the absolute value of x minus 2 to the 5 halves power over the absolute value of x minus 2 to the 1 half power plus that constant over x minus 2 to the 1 half power. Push my paper up a little bit. So what we've done is just multiply through, but instead of using the root there, I just changed it to the exponent 1 half power. And so ultimately what we've got is that v of x is equal to, we can show this is x minus 2 quantity squared, because I can drop the absolute value taking the difference of the exponents there. That'll just be the absolute value of x minus 2 squared, which will always be positive. And then the remaining term is just c over absolute value of x minus 2 to the 1 half. And finally, what we need to do is recall that v of x is just y of x to the 1 half power. And resubstituting that into this equation, you can show very quickly that y of x is the quantity x minus 2 squared plus that constant over x minus 2, an absolute value, and if we want, we could just put a square root there, and that quantity would be squared. And that would be the solution to the original Bernoulli equation.